What you just heard was the sound of the future. And I think I'm going to have to explain that a little. More than a century ago, in 1887, Simon Newcomb, who was then the dean of American astronomy, made an infamous remark. He said, quote, "So far as astronomy is concerned, we do appear to be fast approaching the limits of our knowledge. The result is that the work which really occupies the attention of the astronomer is less the discovery of new things than the elaboration of those already known." Well, of course, very soon after that, in the 1920s, our concept of the universe was completely transformed. First, we learned that the Milky Way was not the sole galaxy in the vast voids of space, but just one of a multitude of galaxies in the universe. And on top of that, we learned the stunning news that the universe is expanding. Well, I guess the lesson here is that it's very dangerous to suggest that we're ever approaching the limits of our knowledge, as Newcomb thought back in 1887. Yet, I have to confess, I had some of those similar thoughts back in the 1980s when I was beginning my science writing career. When I started covering the field of astronomy and astrophysics, I had the dismaying notion that all the windows of the universe were completely open. By then, astronomy had expanded beyond the visible light, collecting visible light with optical telescopes, into radio and infrared, ultraviolet, X-rays, and even gamma ray telescopes. I envied the science reporters who had come before me, who were able to actually see the founding of these fields, because every time a new window was opened, something spectacular was discovered. Pulsars, quasars, all these wonderful mysteries of the universe revealed. I truly thought that I was only going to be there to cover the further details. I was going to be part of the cleanup crew. But then during a series of magazine stories I was doing for Discover magazine in the 1990s, I learned about this new endeavor, which really sounded like a long shot, to build these complex instruments to detect gravitational waves, or gravity waves for short. And as we will learn, these are actual vibrations in space-time that Albert Einstein first predicted with a paper that he published in 1916. And so with this knowledge, and by doing these stories, I thought, oh, I now have the chance, the opportunity to see an emerging field as it's being formed, which led to my book, Einstein's Unfinished Symphony, a title I chose because gravity waves are the last prediction from Einstein's great general theory of relativity that has not been confirmed directly. But this venture is also much, much more than that. This evening, we're going to learn how these new gravity wave telescopes that are now coming online will offer a completely new way to look at the universe, providing information that telescopes that gather electromagnetic radiation cannot provide. We'll learn why the gravity wave data comes as a sound, just as we heard at the opening, not as an image. In a way, our universe has been like a silent movie, only all of these images with no sound. Gravity waves are going to turn us into talkies, finally. We're going to start hearing what the universe has to say as black holes collide or stars blow up as supernova. We're going to learn how this may be the only way possible to make very precise explorations of the physics of black holes and even view the very moment of creation, the Big Bang. This is a new form of astronomy that was thought impossible not too long ago. And it's vastly different from how we've studied the universe in the past, as you'll see. Once upon a time, it was thought the universe ran like clockwork. The sun, Earth, planets, and stars all moved with utter predictability, like a well-oiled machine. With observations, first with our unaided eyes, and then with telescopes, an advance introduced by Galileo, we discovered new planets, stars, and eventually distant galaxies. In 1687, Sir Isaac Newton published his monumental law of gravitation, showing how gravity was a universal force of nature. There was one problem, though. He couldn't explain the origin of gravity. Why is the Earth attracted to the sun? It wasn't until the beginning of the 20th century that Albert Einstein, with pencil, paper, and a great deal of thought, unveiled his general theory of relativity, revealing the true nature of gravity. Gravity, said Einstein, isn't simply an attraction between two objects. It arises from a distortion of both space and time, what is called space-time. Space-time is like a fabric, and what we call gravity is the result of the warping of this fabric by a massive object, like a star. The Earth orbits the sun because it's riding along the space-time curvature carved out by the star, like a ball spinning around a roulette wheel. With this in mind, Einstein also predicted the existence of gravitational waves, actual ripples in the fabric of space-time that are produced by the most violent events in the universe. But no instruments existed which could actually hear and measure these messengers of gravity, which Einstein envisioned. That is, until now. Ladies and gentlemen, please welcome our panel. First, I would like you to welcome Ray Weiss, who is often called the father of LIGO, the Laser Interferometer Gravitational Wave Observatory, which is going to be the focus of tonight's discussion. Ray is an experimentalist at MIT. He has brought two fields of fundamental physics research from birth to maturity. First, the measurements of the cosmic background radiation, the echo of the Big Bang, and now gravitational wave observation. Ray, in fact, invented the interferometric gravitational wave detector, an idea he got while doing a homework problem for the students as he was teaching a course on general relativity. No small feat. Next, I would like to introduce Andrea Lohman. Andrea is both a physicist and astronomer who studies millisecond pulsars, tiny neutron stars that spin extremely fast. And in 1993, a Nobel Prize was awarded to Joe Taylor and Russell Hulse, who discovered a binary pulsar, which provided the first indirect evidence for the existence of gravitational waves. Andrea is continuing this work and is the chair of NanoGrav, which stands for North American Nanohertz Observatory for Gravitational Waves. And this project seeks to build a collaboration with North American, European, and Australian astronomers to detect gravitational waves from the sky via pulsars. Next panelist, Kip Thorne. Kip is a theoretical scientist known for his prolific contributions in gravitational physics and astrophysics. He's one of the world's leading experts on the implication of Einstein's general theory of relativity and has written numerous books on the subjects, including the best-selling Black Holes and Time Warps. And he's garnered prizes and honors too numerous to list, but I'll mention a few. The Lilienfeld Prize of the American Physical Society, the Karl Schwarzschild Medal of the German Astronomical Society, and the Albert Einstein Medal from the Albert Einstein Society. And more interestingly, in his latest career, he's currently co-author and executive producer of a new movie project with its working title being Interstellar, to be directed by Steven Spielberg. And he's also co-founder with Ray of the LIGO Observatory. And last, Laura Danley. Laura is currently serving as curator of the famous Griffith Observatory situated in the Hollywood Hills of Los Angeles, but she's also an experienced astronomer who has had extensive experience, hundreds of hours, making both optical and radio observations at such facilities as the Kitt Peak, McDonald, and National Radio Astronomy Observatories, as well as ultraviolet space telescope observations. Welcome, panel. Welcome to this evening. Thank you. I'd like to begin talking about how we got here to begin with from the past, from the astronomy of the past. Laura likes to describe herself as someone who has retained the childlike wonder whenever she looks up at the sky, and which is actually the way the ancients first studied the universe. What do you remember about your first observations, the way the ancients looked at it?
Everyone is an astronomer in some sense if you've ever looked up and seen anything in the sky, and I think that's just about where every astronomer has started. For those who might have been at the opening gala, there was a song, a chorus saying about nose in the air, because astronomers are always looking up. But it's true, if you are, well, most every astronomer I know just began by the fascination of what is out there, what does it mean, how can I understand it? And you can't touch it. That's why I think people think of it as a domain of gods, because it's untouchable. You can't put it in the lab, you just have to receive the light and try to understand what it is you're seeing.
Well, first that was with our eyes, but things changed around 1610, when Galileo and his contemporaries introduced the telescope. How did things change with that?
The more we've come to understand about light, the more we understand how to manipulate it. And it actually first just came from experience. You all know if you hold up a glass of water in front of someone's face, it will distort. And so materials can change the way light things look through them. And so the idea that using a lens or a curved mirror to magnify and to collect light is really the basis of all that followed. And more sophisticated ways of collecting light, analyzing light, measuring light is really the history of 400 years now of astronomy.
And what do we learn from gathering electromagnetic radiation?
Light, and I will ask for the first, is something we're all familiar with. If you've ever played with a prism, you know that a prism will break light up into different colors, and those different colors are simply different wavelengths of light. Light is a wave, and red has a longer wavelength, blue has a shorter wavelength, and so we can measure the different wavelengths of different kinds of light and understand something about the nature of that light. If you look a little further, and you really tear apart what an electromagnetic wave, what is called, this will come in handy when we talk about gravitational waves. There are a couple things you can learn or study or measure about waves. One is how big the amplitude of the wave is. You know, surf's up, I'm from California, bigger wave, lots more fun. The other is the wavelength, or the space between the crests. And a third is what's called the polarization. You don't experience that so much unless you have Polaroid sunglasses, but it's the angle, the way these little crests and troughs go, what orientation they're traveling. And each and every one of those measurements contains information. It's like information of distant objects is encoded, and it really is quite a lot like encoding information about the source of that object.
What sorts of things? What do you learn?
I can look at a galaxy that is billions and billions of light years away, and well, no, that's not true, but very far away, and measure, for example, its velocity by measuring how the wavelength or the difference between crests has changed based on how fast it's traveling. If you've ever gotten a speeding ticket from the Doppler shift, you know this technique well. Astronomers do that to check out speeding galaxies. But things like the wavelength of light that I was speaking about a minute ago, they all also will tell you the temperature of the object, the chemical composition of the object. You know, really just about, everything we've learned about the things off the Earth have been studied by different types of light. And expanding beyond what our eyes can pick up, the visible, is light from, and I heard in your introduction mention of longer wavelength light like infrared and microwave and radio waves, or shorter, more energetic types of light like ultraviolet light, X-rays, and gamma rays. So each and every one of those, this is a lot of information on this slide, but there's a lot of information encoded in light. And so the trick of the astronomer has been, over the years, to just successively decode the information and figure it all out. And that's the enterprise we're all part of.
And the next thing that astronomy is really involved in is forces. And of course, the universal force, the force that has the greatest effect throughout the cosmos, is gravity. And how did the ancients view gravity? I mean, this is the first thing we learn of as we're born. Yeah. We feel it immediately.
Yeah, even the first sort of understanding you have of all things is that nothing stays the same. Everything changes. And what is the force behind that change? Is there an invisible hand? Are there laws of nature? I mean, that's been, you know, mankind's great quest for as long as the written, and certainly before probably as well. What causes things to happen the way they do? And scientists have now come to understand that there are some fundamental forces, 4 of them in particular. Tonight we're really focusing on gravity, but as you properly said, gravity is everywhere. We experience it all the time. Every time you fall off a log, every time you drop something, you know that gravity is at hand. So,
well, how did Aristotle think about it?
So the ancients thought of it as really matter trying to seek its right place in the universe. If the center of the universe was the Earth, then the more solid, the denser matter would try to get to the center of the universe, and lighter things would try to move to their right place. So rocks would fall and steam and smoke would rise, and that was just the natural order of things. But he made the prediction that therefore heavier things should fall faster. And that was undone, shall we say. Well, people had started to wonder, that's not exactly right. How can we measure that? Can we take what my experience shows and see whether that's true? So I did actually bring a prop here, and this is going to be messy, but I'm going to do it anyway. I am not Galileo, and we're not at the Leaning Tower of Pisa. And in fact, the story of Galileo and the Leaning Tower of Pisa probably is not correct. But pardon me for a moment. It's natural. Again, I was saying that what we see with our eyes gives us our first clue of what the universe is all about. So if I were to, and I'm going to, and I hope this doesn't splat all over here, drop these 2 objects together, well, let's do it first and tell me what you see. Which dropped first? The apple. And naturally, of course, because it's denser and heavier, right? Is that the right answer?
So Aristotle thought, of course. That proved his point.
It makes sense. It's what we all see. It's what we all experience. So in fact, that turns out not to be the case. The apocryphal story, or the legend, goes that Galileo took a cannonball and a musket, 2 different objects, dropped them from the Leaning Tower of Pisa, and saw that they fell at the same time. That's probably legend. It was not really, he never described his own experiment in that way. But he did work with inclined planes, in other words, rolling balls down long sloping planes, and saw that things did. If you put two balls of different masses, roll them down the plane, they rolled down at the same time. And what he really discovered was that acceleration, the rate of acceleration, was universal. All things are attracted to the Earth at the same rate. And that was, of course, completely contrary to the view that Aristotle, the Aristotelian view of the universe.
But we have some proof that the apple and the feather.
We do, and I've put down my little machine here, so let me put this back. This now, the reason, we'll explain it after the video. This will show you what happens. We have to go to a special place, a special environment to really do the test properly. And fortunately, we have been to some special environments for that.
Can we copy the low solar wind and penetrometer drum in the ETB?
This was not filmed in Arizona.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got the...
Beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
A little different than what we just saw.
Mr. Galileo was correct in his findings.
So now, of course, the trick was to pick up the feather, and I couldn't find a feather. The pigeons were too fast, so I got a leaf from across the way. But the principle is the same. And so that is the great recognition that all things in the same gravitational field are accelerated in the same way. And Newton categorized that, was able to write down and codify and do mathematically make it all hang together in a picture that worked for hundreds of years and was very successful and is still successful with our local environment. I mean, we work on scales. I drop an apple, I drop a ballpoint pen, they still fall at the 32 seconds per second acceleration.
So Newton was able to codify this in the mathematics, but over time, there were a few glitches. In fact, this beautiful photo we see here shows some of those glitches. What's happening here that makes Newton a little nervous? Newton would not know how to explain this image.
Well, this is a doorway to the rest of this discussion because it is how we understand gravity today, thank you to Mr. Einstein. And it is, as you said in your introduction, having to do really with space-time curvature. And I love this picture because they are showing something called gravitational lenses, light being bent. You know, light always goes on a straight line. So why would light be bent? Well, it's because straight lines are bent. Space-time is bent by the presence of mass, and that is another entirely different way of describing gravity, and that has success on the kinds of scales and masses that we now are able to probe. Newton couldn't probe those things. He didn't have a telescope that could show this image. He wasn't able to carry out the kinds of measurements to see the deflection, for example, and I will leave this to the further panels to speak about some of the observations we have about gravity now. He just simply didn't have the apparatus. So it wasn't that he was not smart or that Aristotle was dumb. It's just that we are always limited by our ability to measure, to observe and measure.
Well,
that's where we're on the threshold of some new measurements today.
And I can bring Kip here, who is the authority. What drove, of course it was Einstein who recognized some problems with, not through these images, but through other problems. What drew Einstein to want to recast Newton's laws of gravity?
I think the main thing was not observations at all. It was that he had already conceived a new way of thinking about space and time, in which he concluded that time is a personal thing, not a universal thing, that if you move in a different manner than I do and live in a different gravitational field than I do, time for you will flow at a different rate than space. I'm sorry, I don't have a gravitational field yet. So he had been, in his special theory of relativity, if you move differently than I do at a high speed relative to me, for example, I see your clock slowed. I see you squashed. I see you compressed. So the idea of lengths and times depend upon the person and how the person moves.
So each time I start moving, I'm in like a different bubble of space-time than you are.
If you go out there and run around and come back, you will have aged a little bit less than I have.
I like that.
Yeah, yes. Teeny weeny bit less. However, Einstein, in looking at Newton's laws of gravity, saw very clearly that Newton's laws of gravity were totally incompatible with his own conception of the nature of space and time. So Newton's laws say that the gravitational force that the Earth exerts on me is inversely proportional to the distance between us squared, but the distance is measured by whom? By me if I'm in orbit around the Earth, or by the Earth? Well, those distances will be different. And for Newton, it was an instantaneous action at a distance, the instantaneous distance. But if time flows differently for me when I'm moving than for you sitting on Earth, then what is simultaneous is different from your point of view than from mine. So the whole foundations of Newton's ideas about gravity were incompatible with Einstein's concept of the nature of space and time.
It led to a new physical idea of
That's
what
right. So
space and time are.
Einstein had the chutzpah to believe that Newton was wrong and that he was right. And so he said, I have to reformulate the nature of gravity in a new manner that fits with my ideas of space and time. And after several years of struggle, he concluded gravity must be associated with a warping of space and time.
And how would you describe that?
Well, I like to describe it in terms of Einstein's first insight about the warping, what I would call Einstein's law of the warping of time, which says that all things, both feathers and apples, want to live where they will age most slowly. They want to be at their right place, their natural place. So a combination, if you wish.
Like humans, we want to be immortal.
Yeah, that's right. And gravity pulls them there. And so Einstein, in his deeper understanding of this, recognized that time flows more slowly on the surface of the Earth than it does at high altitude. And he said it is because of that there's a gravitational pull that pulls you toward the surface of the Earth. In mathematical terms, if I can get mathematical for 10 seconds.
For 10 seconds, you're allowed.
The gravitational acceleration is the speed of light squared times the rate of change of the rate of flow of time between there and here.
Okay, so that was one
the
prediction.
difference in how time flows.
That was one
That was
prediction.
one prediction. It's been verified observationally to very high precision.
So that atomic clocks in space run faster
Precisely.
than the clocks down here on Earth.
Precisely, and by precisely the same amount as Einstein's laws predicted.
In fact, the GPS that we all use, and we're now becoming quite dependent on, needs to make corrections for general relativity in order for it to work.
If those corrections are not made, it will fail fairly quickly.
So if we didn't have Einstein, we would have figured this out with GPS pretty quickly. We would have discovered it pretty quickly. What are some other predictions?
Well, so Einstein then recognized if time is warped, then space must also be warped because space and time are personal, and my time is in some sense a mixture of your time and your space in a weird sort of a way. And so space must be warped. And he predicted then that the shape of space around the Earth or the Sun must be sort of like the shape of a bowl. The circumference is going to be less than pi times the diameter. If you go down a bowl and up to the other side, you get a longer diameter than the circumference divided by pi. And that then was verified by now to extremely high precision through deflection of starlight by the sun, through the delay in time of arrival of signals that are sent out to a distant spacecraft going near the sun and coming back. So again, a prediction warping of space like the warping of time to very high accuracy.
What sort of
verified.
things have theorists been able to extend beyond the time of Einstein when he made these predictions? What else have we learned since the time of Einstein?
Well, we have understood from Einstein, we have understood that there should be one other aspect of the warping of space and time, and that is gravitational waves. And that is going to be our focus here. And,
so what is a gravitational
and so,
wave?
Well, a gravitational wave, in some sense, is sort of like a water wave. You have a source of gravitational waves. For example, at the center of the screen, you have two black holes that are orbiting around each other and are going to collide a few seconds from now. And you have ripples of waves in the fabric of space and time, if I can talk heuristically, traveling out from those black holes.
Almost like if two stones in a pond
That's
were...
right. Or you just stick your finger in the water and turn
We'd
it
see the
around and
ripples go
around. You
out.
see the ripples of waves going out. But the physical manifestation of these ripples is what I show here. If the waves are propagating from the back of the auditorium through me, the waves will stretch and squeeze space in the manner that is shown here. You stretch horizontally and squeeze vertically. The next half cycle, you stretch vertically and squeeze horizontally. What that means physically is that if we're really out in space, we're not here on the surface of the Earth, we don't have to worry about the Earth's gravity. If you put down two particles at rest out in space with respect to each other, because space is stretching and squeezing, and each of them in some sense rides on space, or each of them remains inertial, they move back and forth relative to each other. That is, inertial frame here and inertial frame there move back and forth relative to each other. Similarly for inertial frames here.
Should I be afraid of being present in space when a gravity wave goes through me? I mean, if I'm stretching and squeezing...
Well, I'm sure gravity waves are going through you right now, and we'll talk later about how strong that is. I wouldn't want to be experiencing this stretch and squeeze in the immediate vicinity of a black hole that's producing it.
What would happen?
But, well, it may be painful. Let's just put it that way. But the stretch and squeeze are very weak, as we'll discuss later, out here on Earth.
Well, what can we learn about these sort of, gravity waves traveling through the universe? What can we learn from them?
There are objects in the universe that are made from warped space and time. I like to call this the warped side of the universe. A prototypical example is a black hole. And this diagram shows you, it's a map of the warped space and time around a black hole. If I take a black hole, imagine it as a sphere here. I take an equatorial slice through that sphere. Then I have a two-dimensional surface, and I want to see what does that surface look like. So I take it away and put it in a flat region of space, say back here in this auditorium. It has to bend down in the manner that you see here in order to fit itself into a flat space. Or another way to say it is that our universe is a brane or membrane in a higher dimensional hyperspace or bulk.
Of course.
And of course.
Another way to say it.
And the purple stuff out there is the bulk, and our universe, the surface of our universe in the vicinity of the black hole is bent in this way. In addition, the color coding shows the slowing of time. At the point where you go from yellow to red, time is flowing at 10% the rate that it flows back on Earth. And right down at the horizon, the surface of the black hole, which is a circle at the bottom there, but it's really, of course, a sphere, time is slowed to a halt. It flows basically infinitesimally slowly. In addition, as the black hole spins, it drags space into a whirlpool-type motion around and around with an angular velocity proportional to the length of those arrows. And so you have this rich structure of the warping of space and time of a black hole. I would like to know, are Einstein's predictions from his theory, the predictions actually made by Roy Kerr using his equations, is that the way black holes really are in nature? I would like to make a map of a black hole observationally, and gravitational waves are the ideal way to do that.
And this is something Einstein never really
he
imagined.
had no idea about that. In addition, other objects on the warp side of the universe that we can talk about as the evening goes on are neutron stars. They're made partly from warp space and time, partly from matter. The Big Bang singularity in which the universe was born, cosmic strings, sort of like rubber bands stretching across the universe that have circumferences that are less than pi times the diameter. And our universe is a membrane or brain in a higher dimensional bulk. These are all things basically made from warp space and time, things that we expect to study using radiation that's made from warp space and time, using gravitational waves.
So gravity waves are going to be
That's
our entryway
precisely.
into these new effects of the
Precisely.
universe that weren't even thought of
Yes.
a few decades ago.
Yes.
Now, you also, as a theorist, do a lot of modeling
Yes.
in order to try, we don't know these things yet. We can't see them yet. We don't have the detectors yet.
Yes.
We're just starting into it. How do we even know what to look for?
So let me just skip over one slide here to the next one. So the gravitation, particularly interesting as an example, is the gravitational waves emitted when two black holes go around each other, spiral together, collide, and merge. This is the most violent event that occurs in the universe because at the moment when the black holes are merging, they emit gravitational waves with an output power or luminosity that is 10,000 times the luminosity of all the stars in the universe put together. 10,000 universe luminosities, and it's all coming out in gravity waves, none of it in light. It's a brief event. It's an event that will last a fraction of a second if these are black holes that weigh a few times the mass of the sun, or will last a few hours if they are massive black holes at the center of a galaxy, but 10,000 universe luminosities. And we understand the waves that are being emitted through numerical simulations on supercomputers. And I'm going to show you a movie of this. In this movie at the top, you see the two black holes going around and around each other as you would see them against the blue sky in our universe. In the middle, you see the warped space and time as they would be seen by an observer looking in from hyperspace or in from the bulk. And down at the bottom, you see the gravitational waveforms. The black holes are going to merge. I'm going to pause the movie so you can admire the black holes colliding. And then the final merged hole vibrates, and the vibrations die out. And the gravitational waveform shown at the bottom carries detailed information about the wild oscillations of warped space and time that occur during the merger. But more generally, the waveforms are going to be much more complicated than this particular waveform. These are just examples of waveforms that would occur if you had a little different orbit, an eccentric orbit, or you had one of the black holes spinning. There's very rich information in these waveforms, and our goal in gravitational wave astronomy will be to measure the waveforms, decipher them, and extract the rich information that is carried by them.
So these are all, in a sense, a language telling us what those black holes are, their mass, their behavior,
right.
Their properties are all encoded in those different waveforms.
And the supercomputer simulations are the things that we use to build a dictionary that tells us this waveform corresponds to what's produced when a black hole tears a star apart, or what's produced when a black hole spinning like this swallows a black hole that's spinning like that. And so we are building our dictionary through simulations, and then our colleagues doing the experiments will see what they see, and we will go to our simulation dictionary to figure out what's going on.
So what are the prospects that we're actually going to be able to do this?
Well, there are 4 frequency bands in which I expect gravitational waves to be detected in the next decade, or the next maybe one of these will maybe take a little bit more than a decade, maybe 12 years, 13 years. There's a high frequency band, which we will talk about, where something called LIGO works, a band between 10 oscillations per second, 10 hertz and 10,000 hertz. There's that's a ground-based detector. LISA, the laser interferometer space antenna, operating in the low frequency band, periods of a few minutes to a few hours of gravity wave periods. Very low frequency band, which Andrea Lohmann will talk about, where she is the leader of the effort, periods roughly a graduate student lifetime. Sort of months to years. And then the extremely low frequency band, where the wavelengths of the waves are roughly the size of the universe, which will be studied using polarization of the cosmic microwave background. So we can talk about all of these at one time or another this evening.
I should point out that though the field of gravitational wave astronomy is now getting quite hot, it actually began quite a long time ago, originating with a man named Joseph Weber, who was a physicist at the University of Maryland. And he actually built the first gravitational wave detector to try to capture a gravity wave. This was back in the 1960s, but he was never able to really confirm a wave. Then serendipity came into play. There were these two radio astronomers, I mentioned them before, named Joseph Taylor and Russell Hulse, who were studying pulsars. And they stumbled upon something very interesting, a binary pulsar. And maybe, Andrea, you can explain a little on how this led to our indirect confidence that gravity waves are actually out there.
Yes. Well, so let me tell you a little bit about a pulsar first. A pulsar is, at its core, is a neutron star, which Kip mentioned a couple minutes ago as one of the objects that we would like to study more deeply with gravitational waves. But a pulsar is a dead, dense star collapsed down to about the size of Manhattan and spinning as fast as a kitchen blender. And it emits a radio beacon. So you got to kind of pause and imagine Manhattan spinning as fast as a kitchen blender. So there's a radio beacon coming out one side of this star, and the star is spinning so quickly, and every time the beacon crosses your line of sight, you see a pulse. That's why it's called a pulsar. And some friends of mine, actually, if we could play that first slide, the top sound on that first slide. This is the sound. These are friends of mine. Michael Kramer and Ben Stappers converted the radio beacon from this pulsar, which has a 3/4 of a second period. So each tick is about 3/4 of a second. They converted it into a sound so we could hear what's actually an electromagnetic wave. But this is what a pulsar would sound like if you could hear it. So they're basically celestial clocks. And Russell Hulse and Joe Taylor, Russell Hulse was the graduate student at the time, got pretty excited about these clocks because they realized that they could do a lot of tests if they could find some of these really interesting clocks. So they got very excited about this binary pulsar. And let's play, before I show you the binary pulsar, can we play the next sound? Because this is closer to the period of the pulsar that they were looking at. This has an 89 millisecond period. And this is about how fast the pulsar they were studying, 1913 plus 16.
Sounds like a galloping horse.
Yeah, someone said it sounded like those drums that you hear. So they got very excited about this pulsar. And then the next slide, if we could go to the next slide, has, oh, thank you. This is actually a graphic from the Australia Telescope National Facility, and here you see an image of these two, one of them's a pulsar, and it's spinning around another object, which we believe to be a neutron star. And you see the radio beacon, that blue beacon, that's the radio beacon shining out and emitting these pulses. And you also see these two massive objects rippling the space-time around them. And just play it one more time, because it's so fun. And so you see, if you watch the green grid now, don't get too caught up in the cute yellow stars, watch the green grid and notice that you see these ripples of space-time propagating away from this system. And what Russell Hulse and Joe Taylor realized is that this system, the gravitational wave would actually be taking energy away from the system. So actually, over time, these two pulsars should actually speed up and start going faster and faster around each other.
They're actually coming closer together.
And that this was predicted by general relativity. And so over the course of the next 30 years, they and another colleague, Joel Weisberg, measured this shrinking of the orbit. And I have a graph to show you. The next slide, if you show the next slide, I think it has a graph here's the most scientific graph I think we're going to show tonight. You see on the solid line, I'll just tell you, the solid line is the actual prediction of general relativity, and the dots are their measurements. So these are Russell
Smack
Hulse, Joe
on.
Taylor. Yeah.
Smack on.
So in other words, and you can see the year going across the bottom, so you can see that took them 30 years to make that plot. So this is the orbit shrinking by about 3 meters a year.
And that's what's amazing. The astronomers could actually measure through this that the pulsars were, the orbit was shrinking 3 meters a year.
Right. Exactly right. It's about 2 million kilometers across between those two pulsars. And out of 2 million kilometers, they could tell that it was shrinking by 3 meters a year. And that's what they're measuring. And so they measured, they didn't detect gravitational waves, but they measured this shrinking of this orbit exactly consistent with Einstein's prediction of gravitational waves.
And gravity waves was the only way to explain the loss of energy from this system.
It is the only way to explain
So
it.
that's the indirect evidence for gravity waves,
Right.
which led to a Nobel Prize.
Right.
Because it was so beautiful, smack dab
lovely prediction.
accurate. But you're now extending this work.
Right. So, and I have colleagues, by the way, who say, why do you study something that doesn't exist? And I say, well, we really think it does. We really have reason to believe it does exist, but we don't actually have direct evidence of gravitational waves, which is why all this is so exciting. But the way that my group and other groups, the European Pulsar Timing Array and the Parkes Pulsar Timing Array, are aiming to continue to extend this work is to actually use that pulsar. So if let me show the next slide. There. Okay. So now we're moving outside the pulsar system. So now instead of thinking about the waves that are caused by the pulsar or the environment around the pulsar, now we're thinking about gravitational waves that would be caused by some other system, like this massive black hole binary. You see these two black holes spinning around each other. You can tell they're black holes because they're black. They're two black holes spinning around each other, emitting these gravitational waves. And now we're using the pulsars, far, far outside of that system to detect the gravitational waves from that system. So now we're using the pulsars to detect some other gravitational
So
waves.
pulsars are your instrument.
That's right. So pulsars are my detector. And I have this galactic scale detector that was given to me by the universe. It's lovely. And so the pulses, so those these very these lines from the pulsar to the Earth are meant to represent the electromagnetic radiation. So these are the pulses that you heard or that you imagine seeing when you see this pulsar. And so you imagine that as these gravitational waves are moving through the space in between the pulsar and the Earth, they would perturb these pulses somehow. So the pulsar that's otherwise very regular and very much like a clock would gain an arrhythmia, if you will, from this gravitational wave. So it would seem like a metronome that no longer quite functioned correctly. And so that's actually the signal we are looking for in these pulsars. We're looking for an arrhythmia in a collection of pulsars. Now, we don't just have two pulsars. We actually have, I did that for the purpose of a nice, concise graphic, but we actually have about 30 pulsars. So we actually have something like 30 pulsars distributed around the galaxy, and we're looking for coordinated signals among these pulsars, which would be indicative of a gravitational wave.
In a sense, some of them getting a little faster because of the gravity wave, some going a little slower because of the gravity
Yeah.
wave passing through.
Both faster and
slower.
Either faster or slower, arriving too early or arriving too late.
But you have to be really confident that you know the timing of those
Right.
pulsars. Is that part of your
That's
problem?
sort of the whole game. That's sort of all of what we're working on right
Are
now.
pulsars
because
that stable?
They seem to be that stable. There are some of my colleagues would argue with me on that. They seem to be extremely stable. The things that are our biggest challenge right now are things like the interstellar medium. It turns out there are huge numbers of free electrons in between the pulsar and us in this slide. I left them out of the slide, but there are all these electrons that also cause delays in the pulsar signal. So they could also cause the pulses to arrive a little bit early or a little bit late. We have ways of subtracting those those deviations. And the other thing that's very nice is that there's no way you can get these electrons to produce the sort of signal that we would hope for from a gravitational wave. There's actually a very specific shape that this group of pulsars would show from a gravitational wave, and you can't reproduce it with some kind of delay from a cloud of hydrogen intervening.
By a special shape, you mean there's some sort of correlation between what one pulsar is doing and the other is doing?
Yeah, if we actually go, can we go to the last slide? I think it's my last slide, number 12. Yes, so here's the actual shape that we're looking for. And so the other way, let me try to finish a sentence. This is a picture of the shape you would expect to see in the pulsars if you're looking for things arriving late or arriving early. And these two lobes here are actually supposed to be negative lobes, but I can't figure out how to graph that. So if you imagine all these pulsars arrive early, and all these pulsars arrive early, and all these pulsars arrive late, and all these pulsars arrive late, that would be the shape you're looking for. So in case that's not obvious I don't think it is obvious how to translate that into space. If my group of pulsars is all over the sky, then I can divide the sky into 4 quadrants. And I would expect all these pulsars, the pulse from all these pulsars to arrive early, the pulse from all these pulsars to arrive late, the pulse from all these pulsars to arrive early, and the pulse from all these to arrive late. And furthermore, there's another shape superimposed on that, which is that the effect is greater at my feet. This is imagining a gravitational wave is coming up this way. The effect is greater at my feet and reduces as you go up here. So there actually are a number of very specific properties of the shape. And if we detect that shape in these lateness and earliness of these pulsars, we know that we've got a gravitational wave, because there's I couldn't fathom creating the set of hydrogen clouds that would produce that sort of pattern.
Okay, so we know gravity waves affect not only space but also time, and your measurements are using the universe, using real live objects out there, and looking at timing differences, but we're also going to be hopefully looking for spatial changes through the detectors on Earth. Ray, you're dealing with another way of looking for these gravity waves through instrumentation right here on Earth.
Yeah, we certainly are. And I'd like to see that first slide, because it's a lot of people doing it. It isn't just a few. Okay. The reason why I want to show this slide is because there's a very important group on this slide, the University of Mississippi, and I'll tell you why they're important. They have set up a very beautiful exhibit, especially Marco Caviglia, down on near Wall Street. I forgot.
It's on Broad Street.
On Broad Street, right.
Right near the New York Stock Exchange.
And you can, if you go there, actually experience a lot of what I'm about to tell you. So
it's a
and it's
hands-on
free
exhibit.
and it's opened every day. I
Yes.
think that's the nice thing about it. Now, the problem Kip made it sound easy. And the problem really is on this.
I thought it was going to be easy. It's your job to make it happen, and you're very talented.
Yeah. But that talent has nothing to do with it. This is the problem.
Theorists or the optimists, experimentalists know
Well,
what's
the problem,
actually happening on the
let me
ground.
highlight the problem, and give me my chance, okay? And the problem's right there. It's a little bit clouded. When somebody says that you're going to measure a stretching, the thing that Kip described, a stretching of space, and one way of talking about that is called the strain, and that's what this quantity right there is. And when a number which is death-defying, it's 10 to the minus 21. Let me explain the 10 to the minus 21. Many of you learned in high school about decimals, 0.01, that's a hundredth. Well, this is not anything like that. That's 0.0 with 21 zeros, and then you hit a 1, okay? It's really almost impossible to think about. It's tiny. That's the biggest that people will contemplate, that they will give us a gravitational wave. And Einstein made that number, by the way, himself.
We should explain first that when those black holes collide or the supernova explodes, the gravity wave is very strong. But the reason this is small...
Unfortunately, that's us. And see, when Kip asked you, or you asked Kip, would you be destroyed by a gravitational wave? I was saying to myself, wouldn't it be pleasure if you were? This would make that so easy, you see.
But there's
But
a good, we're lucky to be in a boring section of the galaxy.
Yeah.
Gravity waves diminish and lose power the farther away they get
Well, they
from the
actually do
source.
something very important, and this is important later on, but it may be in the discussion. But they are a little different in the electromagnetic waves that you see in ordinary astronomy. They don't go down in power, they go down in power, but our measurements, as you will see presently, measure the amplitude of the field. They measure that h. So consequently, they go down as 1 over the distance, not as 1 over the distance squared for our measurements. That's actually very important when we get to the end of this. You'll see. Let me show you this, what the number really means, so that you get a little appreciation of this 10 to the minus 18. Well, I didn't mention what it was. When you build a big detector, and we're talking about a detector that is 4 kilometers big, the endpoint motions of that detector will be about 10 to the minus 18 meters. And I want to give you a little feel for what that is, and that's what this slide does.
That's the change you're looking for.
That's the change that comes about from a that's a strong, poopy gravity wave. That's a really zipper, You'll see that as you go down this thing, we're going to wind up at the sensitivity of LIGO at 10 to the minus 18. But you have to go through a lot of stages. You go through a human hair, then you divide it by 10, another factor of 100. You get down to the wavelength of light, maybe. That's a micron. That's the name for that particular dimension. That's still not good enough. You get down to maybe another 10,000 you have to divide by, and that gets you to the size of an atom. We're still not there. Still a factor of 10 to the 8, 10 million, 100 million away. So you have to say, well, what's the next thing we measure, or we know about, is the size of a nucleus, the inside of an atom. And that's still not it. We have to go 1,000th the size of one of those nuclei of an atom. That's tiny. And that has to be measured on a separation of about 4 kilometers. So when people started talking about this, they thought we were quite crazy. I'll be quite blunt
And for
with you.
good reason. You're trying to
And
detect
my
a
colleagues
length
at
change.
my university were very skeptical. It took them a long time to come around. Now, people at his university, at Caltech, were a lot
much more
more
gullible.
They were. Anyway, these are the places where crazy people are doing this. And they're distributed around the Earth, and the reason for that is that if we, and we will, detect gravitational waves, the way we will find out where they are and the way that we will do science with them is by having detectors all over the world. And right now, there are 2 in the United States, and I'll show you those presently. There's another one in Italy that's about as equivalent, and that's a French-Italian thing, and there's a smaller one in Germany, the GEO detector. There's a smaller one in Japan, which is being built bigger. And we're hoping very much that the Australians will build one also. And what that will do is, by the way having these detectors all over the world, will allow us to do timing measurements so that we can determine where the gravitational wave source is. So for example, if a source is in the east and hits LIGO, it's to the west and hits LIGO first, let's say there, it will hit Europe later. And that timing difference might be tens of milliseconds or something like that. And that will give us the information, ultimately, if you have enough of these detectors, where that object is in the sky. And that's very important to be able to couple back to your astronomy. You see, the one that actually conveys the information about what the sources are. So let me go on. This is the Italian detector. This has a nice feature that right there, this is a big bunch of tubes. We'll talk about them more. They're evacuated, and laser light goes back and forth inside of them, and I'll explain that better in a second. But this is just a pretty place. And here is, for example, a place where Michelangelo got much of his marble right up there. Now, we were told that.
And also, this is just south of Pisa.
Just in Pisa, yeah.
And in Pisa is, in the cathedral, is where Galileo first talked about determining his some gravitational experiments.
Well, he was impatient in church and watched the pendulum go back and forth on the chandelier. I don't think he was listening very hard. But here are the 2 LIGO facilities. One is in a beautiful area of Washington State, and this is 4-kilometer arms. And
why the shape?
Well, we'll get to that.
Okay.
It really has to do with the picture Kip showed. If you remember Kip's picture of the expansion in one direction, transverse to the gravitational wave is coming down, and we'll see this again in a second. Let's say it's coming down on that picture. And what it does is stretches or it changes the time that light takes to go down one of the arms relative to the other. And then a little bit later, those signs flip.
Well, did
And,
we see
that-
the
and the
same
thing is
picture
they're-
in Andrea's?
And Andrea's picture, that's right.
Picture, you saw the same thing.
Same thing.
One arm is stretching while the other is compressing. So
And the thing is that when you measure a strain, this is now for experimenters, why do you want it so long? That's maybe the other part of the question. Is, why don't you do this on a teeny-weeny thing?
it looks
on
like a
table?
particle physics
Yeah, I
experiment.
know, and it got terrible expensive because of that, okay? The thing is that the reason is that our instruments measure distance. And the gravitational wave is constant in strain, which is a change in distance divided by a distance. So consequently, if you want something to measure, you would like to make the separation of these things as big as you can, up to the point where it's big. Well, if you could go to a wavelength. And in LISA, for example, could probably do that for low frequencies. But now the thing is that the bigger the thing is, the easier it is to do the experiment. That may sound peculiar to you, but in terms of the technology that's used, it becomes easier.
So why stop at 4 kilometers?
Well, because you can't find places that are
No,
10
come on, we
kilometers,
did a side
and it
survey.
costs too much money.
Great Salt Lake Desert. You and I went out.
I know, we
ourselves.
went all over the place trying to find
We
10.
found ourselves a great site.
We found sites in Maine,
I
even,
think,
you know.
I think
mean,
the
okay.
big problem was money.
It's money. And that's
So-
why
so you make
putting it,
compromises.
look, Marcia, that's why putting it in space has a certain attraction. And it's a good attraction until you look at the rest of the cost. Okay, I mean, you would not want to start in space.
But it's also why my experiment is such a
Your
good
experiment's a
idea.
cheapie. That's a good one. Yeah.
Well, but her arm lengths are
Yeah.
unbelievably bigger than ours.
Oh, yeah.
The universe gave her the pulsars free.
And that's why, if you look at the universe and you say, let's look at what happens over the length scale of 10 to the 10 years, or 10 billion years, that's the one with the biggest effect, okay? The one that you showed in your slides of the cosmic background. Anyway, so there are 2 United States detectors, the LIGO. One is in Hanford, one is Hanford. This one's in Louisiana, and it has these critters. And it has lots of birds that really actually populate those moats very quickly. It's amazing. You don't realize that birds get around. Why is this that fish get into those places, that moats that get dug up? It's because of the fish roe that are in the claws of the birds. And that's how it happens that you get fish within a year after you dig a hole.
So could you go through a little of how this works?
Well, we'll get to that. That's coming now.
Within time,
she's
right?
right on
Within
top
time.
of me. Okay, I got to get going. Huh? All right, so the way it works is in this picture right here, and let me walk you through this a little bit. It's a little complicated. I'll be a little too fast, and if you will have a chance to ask questions later if you want. But here's a laser, and here are those long arms. That's one arm, that's another arm. And the way it's arranged, and there are some ideas in here that came from a very clever man named Ronald Drever, and that's one of them. We'll get to that. And here's a laser, and it sends light into a beam splitter. It splits the light and makes it spend part of the time, half time in there, half the time in there. They both are the same.
So the light's bouncing
the light's,
back
the
and
light's
forth,
bouncing back and forth. Let me say it carefully. The light is split here. Half of it goes this way, half of it goes that way. Then they spend equal time in the 2 arms, the light beams. They bounce back and forth, and they come out again. And then you arrange it so that the light here, going back to the photodetector from this thing, which is the stuff that's coming out from this arm and that arm, cancel. And that means all the light goes back to the laser, which is sort of nasty. So you put another mirror here. That's a mirror that Ron Drever invented. And that mirror then reflects the light back in and makes it so that all the laser light that is generated, none of it gets reflected by that mirror. All of it, due to interference of light, gets put into the interferometer. And I want to show you that in this picture.
So
This
you're an
picture is
energy conserver.
What?
You're an energy
That's
conserver.
right. Well, yeah, I wish we were really, but this shows you what if you went to the site and actually saw what was going on. You'll see here. This is that cavity getting filled up, and light there is light getting into that cavity. Now, all of a sudden, light will go into both cavities, and this gets very, very bright. And that's the moment when you've got everything lined up, and you notice this light is disappearing. That's the light that is reflected by the interferometer. This light is the light where the gravitational wave would come out, And unfortunately, it doesn't show this what I wanted to tell you because of the fact that this is a saturated detector. But that scene, which you just went through, and I wish I'd had a little more time to explain, is what's called locking up the interferometer. And once you get it into that state where all the light from the laser gets eaten up by these mirrors, in effect, that's when you are ready to detect gravitational waves.
And basically, if I could simplify, you are having in a normal no gravity wave mode, no signal.
Right, exactly.
And if a gravity wave goes through, suddenly the arm lengths change, the laser beams don't quite cancel out each other, you get a burst of light. And that tells you
That's right.
there's a signal.
That's exactly right. Thank you. You help a lot. Let me see if I can show you the next thing. These are now a set of vignettes of the apparatus. So you can, yeah, this is what the beam tube looks like. And this is just a guy. This gives you the scale, that's all. That's a guy inside that tunnel, and he's doing things. But this I want to stop at. This is, you see, my august colleague here, who makes a living out of being a theorist, you see, and writes big books and is very famous. He also does gut work and scut work and junk. And here is a piece of work that he did that was actually wonderful. This is a baffle that was put inside these beam tubes to keep the light from scattering down the beam tube, and was a deep worry for us because we were worried about laser light going down the beam tube and the thing looking very bright. Like in every telescope and everything, you always have to worry that you have scattered light that gets back into your detector somehow. So Kip sat and he did the calculation. He invented this serration, this thing that looks
So
like a
Kip,
bunch of
you're
shark's teeth.
You're
right
a
there.
secret experimentalist?
Yes, he is. He can't deny it.
There's nothing more fun than trying to
All
analyze an
right.
experiment.
So I had to tattle on you, Kip.
Thank you.
Ray, why a sound? Why, when we get this signal, and we heard at the beginning of the program that what we are going to hear coming out of this is a sound. Why
I'll get to that in a
is
second.
a signal a sound?
Because I'll get to that in a second. You'll have to give me a few more slides.
They do have to go to bed tonight.
I know. So let's go right to it. Let's go right to it. That's what the inside of the place looks like, but let me get right to it. Keep going.
And it is like a particle physics
This is what one of the
experiment.
mirrors looks like. That's just a big piece of glass.
All that equipment just to discover 10 to the minus 18th meter change.
And here, we're going to get to your thing in a second. Now, this is an important slide, unfortunately. It tells you where the problem is. And this is the sensitivity versus all the different things that keep you from getting the sensitivity. And this is the quantum noise of the light. This is just the fact the ground is shaking, that limits that. And here is just the fact that the system behaves, it's at room temperature. And everything shakes at room temperature due to the fact of thermal excitations. And by the way, this is the sound part. We'll get to the rest of it. This picture goes from the bottom of the piano, which is right about there, 30 hertz, all the way up to the top of the piano, about 3 kilohertz right there.
I understand that you're even, I mean, LIGO can even detect the waves
Oh yeah, we
hitting-
see the ocean waves and we see the earthquakes all over the world. Here's what it actually comes out of the instrument. The same kind of picture. I just want to show you that because you're going to hear it in a second. This is the actual noise. What you saw in the other picture was a prediction. And it turned out we succeeded in getting to the prediction, which was a big triumph for all of us. That this picture right there, the performance of the instrument, is pretty close to what we thought in the beginning.
How long has it been working now?
It's been working 3 years.
3 years.
Yeah. And
So
now
it's in
I
a-
want to I do want to play this for you. And the gentleman who is running this has to play this for us. And that is, this is to train your ear very much on what you heard in the beginning. I hope you all heard that. That happens to be the sound of 2 neutron stars, or 2 one or 2 solar mass black holes going around each other. It's the same.
Why that distinctive sound? What's happening?
Well, what's going on here is these are pretty much what this picture that Andrea showed. It is the 2 stars, and it's the Hulse-Taylor objects at the end of their lives. That's really what it is.
They're finally,
They're getting closer and closer and closer and closer, and they bop into each
so
other.
it's whoop.
The 2 black holes I showed the movie of will do the
Yeah.
same thing, except a little lower pitch.
Lower frequency. And now I'm going to challenge you. Okay? What you're going to hear is this thing, which is the actual instrument noise. And that, in spiral, is buried in that noise. I want to find out how quickly, or not how quickly, when you can hear it.
This is real life physics.
You got it. Good. That's it. Thank you.
So you have to dig
Now,
that
that's the
signal
whole challenge. You
out
have
of
to
that
dig that
noise.
out. And let me tell you something important. Your ear is a very good detector. It takes a lot of computing to get that, what you heard, out of that noise.
Are you going to be having like computers working 24
Well, they
hours a
do.
day to try to dig that signal
Oh, yeah,
out
and
of that?
there is that much of those 50 institutions with 500 people who you saw on the very first slide. I didn't tell you that at the time. Are people doing this? We have got a huge number of
So this
people
is
interested in
the
this
ultimate
field.
collaborative venture. So how are they going to divvy up the Nobel Prize?
Oh, leave me alone. That's just,
The inventor of the technique will get the prize, and it's not clear who else.
that's baloney. All right, you see, I overdid it, but we're done.
So what kind of different events and sounds are we going to hear from this?
Well, that's it. I mean, this slide has other things on it, but I think let's leave those go unless you really want to know more about them. You see what it is, this instrument looks for not only the binary coalescences, which are these fancy words. It looks for things that go bump in the night once in a while, like a supernova, but it also does things which, for example, and we're starting to do that now, where we're looking at the signals that are developed by the instrument and comparing them to signals coming out of radio telescopes and out of optical telescopes. In fact, there's a very big industry now in astronomy that is looking to look at transients, things that are once in a while, things that happen once in a while, and they're comparing their records with the records coming out of this instrument. So we are beginning to sniff at the astronomy.
So there's going to be a lot of coordination.
There already is a lot of coordination, but it's going to get better and better. The other kind of sources is, in fact, Andrea's source. They will radiate gravitational waves on their own. They may be a little bit oblate, they may be look like American footballs, and when they do that and rotate, they radiate gravitational waves, and very interesting ones. And then lastly, there is another source, which is the fact that the universe itself, the early primeval universe might have generated gravitational waves different than the ones that Kip talked about. I mean, the very early ones everybody now thinks might be there came from inflation, which is a particular model of the initial moments of the universe. It could also be that during that inflation and a little bit after, other kinds of gravitational waves were generated. And they will come in, and they're coming in all the time, and our detectors, if we have multiple of them, it'll be a common noise in both of the detectors, or all 5 detectors that are operating, and you look for that common noise against the intrinsic noise in the detectors themselves. And you do that by something called cross-correlating the detectors.
And how far back is that going to allow us to see?
That's 10 to the 10 years. That's 10 billion years. That's where that comes from.
And that's even, I mean, in a sense, it's going to tell us something about the universe even better than, or farther back.
Well, yeah, I know what you're alluding to. You're alluding to, I mean, what Marsha is talking about is that we are bathed by electromagnetic radiation that comes from that primeval Big Bang. That's something, in fact, everybody who turns on an FM set gets, if they listen between the stations, they hear a little of that. The little bit of the hiss and the
cosmic
noise.
background
Yeah, there's a little
noise.
If you have a good
music.
FM set, you get 5% of that might be the cosmic background. Okay, but there's a thing that originated sort of 300,000 years after the explosion.
We can't really see beyond that. It's like
But
trying to look into the
you
sun.
can look beyond that with these.
With
you can
the
look
gravity
all the way
waves.
back.
And the reason being, gravity waves aren't.
Stopped by anything.
Stopped
They're also
by
very hard to detect, but you get a bonus. They go all the way back.
Electromagnetic radiation gets sort of
Yeah.
caught in matter and gas and everything through the universe. Gravity waves go right through as if it's not there.
And that's another thing we should make more of here, because, I mean, even in ordinary astronomy, I mean, not this very fancy stuff of primeval cosmology, the thing is that you are looking inside. See, I mean, ordinary astronomy, with electromagnetic astronomy, looks mostly at the surface of things. And with this kind of technique, if you ever see a supernova, or a star that has exploded, the signals that will come to our detectors will be those things that are going on deep inside that star that exploded. You can't go in with electromagnetic radiation into that. And that's was one of the selling points to many of us. And I might as well say one thing, as long as you keep letting me talk, is that
I have
to us...
no control, Ray, no control.
No control. The thing that is really the challenge to all of us is, I think, the thing that Kip talked about earlier. I mean, I think that it's not the discovery or, quote, the measurement of gravitational waves. If you asked me why I'm in it, if you asked me that, you would get the answer that I'm interested in what is strong field gravity really like. That place where gravity has curled up space-time in such a way that Newton can't touch it.
And
That's the
and
brand new
Einstein-
thing here.
And Einstein can't touch it. There is this region in which we're still struggling with the union between quantum mechanics and
Well,
general
be careful with that.
relativity.
I don't think we're going to go that far. I think we're clearly in the Einsteinian realm. Yeah.
You will with the radiation from the Big Bang,
Yes.
but not with black holes.
Yeah.
So this is one way to perhaps get observational evidence that will help those like string theorists who
Oh,
are
yeah.
trying to struggle with
I think
finding
there
that
it-
theory of everything.
In my guess is that will come from the cosmic background polarization experiments. That's where I think that will come from.
What about possible surprises? With every window we've opened, there's always been a surprise. With radio, we had pulsars and quasars. With X-rays, we finally got evidence for black holes. What's the possibility?
Well, it's always held out. And if you look, I mean, the thing is, what we're talking about here are, let me just put it in my own language. They're the buckshot questions and they're sharpshooter questions. and we're talking about the sharpshooter questions here. And you're asking about the buckshot questions, okay? And they're the ones that, you don't know what the hell you're going to get. I mean, it's just something. And I guarantee you, I mean, if this field is going to be like any other field, as you said yourself, it's going to have some buckshot.
But that's one of the things that drives astronomers at Caltech, like Sri Kulkarni, optical astronomers, to be focusing on this field now.
Yeah.
Because they see the big payoff is discovering something completely new that they can do jointly with you.
Right.
Because you bring a way of seeing the universe that is so radically different from their way, and yet if the two of you can see something radically new simultaneously, and bring in the radio astronomers, and bring in the X-ray astronomers, the gamma ray astronomers, and the neutrino astronomers, going after the same thing that's totally unexpected, it could be a whole new world.
Yeah, and I fully expect this will happen.
I know that we want to open this up to some questions from the audience, because I know you have many. I do want to first say, to reiterate what Ray said, if you want to learn more, I highly encourage you to go to the free exhibit set up at the Broad Street Ballroom, 41 Broad Street in Lower Manhattan, open through Sunday from 10 till 8 at night, and you'll actually see how the interferometer works. You'll be able to play with it. They have a mock-up model. You'll be able to visualize space-time and actually play a game, an interactive game to hunt for black holes. My husband won because he found all the black holes and got a free laser pointer.
Oh, wow.
So they are giving out prizes, so go and try to find those black holes. Perhaps we can have the lights up, and we can perhaps in our last few minutes get a few questions from the audience for asking what you're interested in from tonight's discussion. Can we have some house lights perhaps to see? We're here with all the spotlights, and we actually can't see you.
Oh, there, I see some questions.
Do we
You do
see
see
some
some
questions?
Yeah, I see 3 hands.
Oh, wow.
Hands, okay.
Oh,
I didn't know if we
one's
could
got
have
the
a few
microphone.
house lights here. We'll have a question right there.
Okay. If you had your druthers, how big an instrument would you make? And is the distance that you can make the arms affected by the curvature of the Earth?
Oh, that's a very good question. Can I answer the second part first? It's very seriously affected by the curvature of the Earth. In fact, that's one of the reasons why, you can just imagine sitting on the Earth and you're hanging pendula, which is the way these mirrors are suspended, and they're not hanging parallel. because of the curvature of the Earth. They're hanging like this. And that causes troubles. So that's a reason you don't want an infinitely big detector, but you can deal with that. No, the thing is, this instrument is big enough to do what we think is the science that we need. I think the next step really would be to do the longer wavelengths in space. And that's a project you may have heard about. It's a joint American and European project called LISA. It's called the Laser Interferometer Space Antenna. And it's very much the same idea. It's using laser timing between 3 satellites. And that is a project that is being considered. A lot of work has been done on it. And if it goes, it will probably go in the 20s of this decade. I mean, 20s of this century.
2020s.
Yeah, 2021. I don't know exactly, but in the 20s. Yeah.
But of course, you go even bigger and you have
And you have
Andrea's
Andrea's thing, which is,
There's a question over here.
The universe, as I understand it, is utterly bathed in electromagnetic radiation. It must also be bathed in gravitational waves. Am I correct?
right.
Where are they? Why haven't we seen them?
You're not working hard enough. They're very weak, and you've got to really feel the vibrations a little more effectively.
I'm sorry, I would like to follow up with one thing. Were there any gravitational waves detectors working at the time of supernova 1987A?
Yes, do you mind if I?
Please.
Yes, there were, not the very best ones. And that's a really unfortunate part. It would have, let me give you a little evolution from the time when
From what I understand, there were bar detectors.
Yeah, well, that's what I want to say.
Yeah.
They weren't the best bar detectors. That's the unfortunate part. You see, what was on at the time was an old Weber bar running in Rome or somewhere in Italy at a level which was far too insensitive to see. And unfortunately, it was a missed opportunity for all of us. The laser gravitational wave detectors were not yet built. They were not yet sensitive enough. If it had happened in this epoch, we would have seen it for sure.
And actually, there was a more sensitive bar at Louisiana, and they were down at that time to improve their sensitivity while that event went on, and they're kicking themselves now.
But in the frequency band that Andrea Lohmann's system operates in, you have waves on all the time. You're going to see more than one at a time.
Right.
How many will you see simultaneously?
Well, you mean how many sources will we
Yeah,
see
yeah.
simultaneously? Yeah, that's a matter of debate. The thing that people talk about the most is seeing an ensemble of massive black hole sources. So many, instead of just that nice, ripple in the pond that you see, if you imagine sort of many of those sources propagating at the same time, many of those ripples from all different directions, you would actually expect, something more like a crinkling. You expect space-time to look something more like this. This is actually about the right spectrum, by the way, because the long frequency, the long wavelength things are higher amplitude than the short wavelength things.
So there's the ideal, and then there's the real.
Yeah, but we
world that
do.
you have
There's
to deal
some
with.
nice work by Alberto Sassana and Alberto Vecchio recently that shows that at the high frequency end of the place that we're sensitive, we would expect to see 1 or 2 bright sources dominating our field. So what I actually expect our sources to look like is an overall crinkling plus a few very bright sources at the high, what I call high frequency end, which to them is extremely low frequency.
Well, basically, it gets down to we haven't seen it because we're only now, in this epoch, developing the instrumentation for the sensitivity to be able to see that sea of gravity waves that is reaching us. Like Galileo could not see the X-rays from Cygnus X1, the black hole binary. He didn't have the instrumentation. You have to reach that level of technology, and we are now reaching the level of technology.
It's in fact the story of doing relativistic gravity, just exactly what you're saying. Every time there has, and this is not that people are lazy, they have the tools. Look, I'm not being critical, Kim. It's the fact that
Theorists just lean back and while you do.
But what the fact of it is just exactly what has to do with technology. I mean, technology development is the thing. Every time something new comes along, and you look, a laser was, or an atomic clock. And those are the two major developments that have changed everything.
And hasn't LIGO actually improved things like the smoothness of a mirror, the efficiency of a
we
laser?
give back. We do give back. But
Yes.
the thing is, but the important thing is it's technology development that makes things possible, which Einstein never conceived of that technology would catch this. Although, by the way, he was a person who watched the technology. He knew about atomic clocks. At the end.
Hey, he invented a refrigerator.
Well, he did a lot of stuff, right? And he got mixed up with a gyroscope. I mean, a lot of things happened. Yeah, just saying. But the thing is that the technology development is what has made it so that you can do these very hard experiments. And if there is any new kinds of things in atom interferometry or any very new precision techniques, if they make sense, that will always push the development of more critical precision experiments.
Andrea, you had.
I just want to say something about your very nice question about 1987A. It illustrates something about the various detectors we've talked about that I don't think we've mentioned, which is that these detectors, the Pulsar Timing Array and LIGO and LISA and the Cosmic Microwave Background Experiment are all complementary, actually. So the supernova is actually completely undetectable by pulsar timing arrays. We're not sensitive to that frequency, whereas LIGO and LISA are. And then there are other sources that, I can detect the massive, I make it sound like it's me. Pulsar timing arrays can detect these massive black hole binaries, like 1 billion times the mass of the sun, whereas those are mostly outside of the range of LIGO.
Very equivalent to going from radio to X-rays.
Right.
All of these different techniques are going to cross the spectrum of gravity wave
So I
events.
think it's interesting to note that from the longest wavelength radio waves that electromagnetic astronomers study to the shortest wavelength gamma rays, it's 22 orders of magnitude, 22 factors of 10. The gravity wave spectrum begins at the high frequency gravity waves are the same as low frequency electromagnetic waves. And the gravity wave spectrum goes down 22 orders of magnitude. So you have gravity wave spectrum, 22 factors of 10 in low frequencies, and that's where the electromagnetic spectrum begins, 22 factors of 10 in high frequencies. It's fantastic what a range we span the two different techniques.
And so I do expect surprises.
I think I
Another.
would just add to that also, since I have to represent the other side, the non-gravity side, is that it's sort of like getting a new sense. So if you've been deaf all your life and you've seen the world, and then suddenly you can hear, for you to even understand the connections, I mean, you may have seen a bird, but never even conceived what a bird might have sounded like. So it gives a completely different, and complementary most definitely, but different way of apprehending the universe that when synthesized will give a picture in full. But it's fundamentally a different way of understanding. It doesn't mean finding a better way to understand or figure out what it is. It's really getting a whole new sense of what is out there and what we can learn.
Yes, back here.
How many, if I understood this lecture, signal from gravitational waves must be at the same times in whole network, yeah?
Yes.
And of course, how many signals really, because all year you have noise, how many signals you have in year, 1 times, 2 times, or less?
Okay, that's an interesting question. Thank you. Let me try to answer that. First of all, there's only one source for which we can answer you properly, okay? And that is the neutron-star binaries. Those are the Hulse-Taylor objects. I can't even answer you in a definitive way for black holes at this moment. We all expect to see signals, but let's stay with neutron-star binaries. For that, we both can calculate the amplitude, and we can calculate the number of objects that are in the universe that will, at the time when we were able to observe them, will collapse and make those little chirps that you heard. So I'll give you a number. The number that now people know both the amplitude and the rate of the events, and that's what you're asking about, is in the run that was made by LIGO, and the LIGO and Virgo together, really, but the expected rate, now that we know better, was about 1 in between 10 years to 30 years.
That's in a search that you've already done.
And in the run we have made, with the spectrum that you saw in the slide I showed. That was a 1-year total accumulated run. Now, we could have stayed on for 10 or 30 years, but I don't think people have that kind of patience. So what instead we're doing, and part of the proposal of the initial proposal of LIGO, was to build it in 2 stages. One stage, which was to show the technology would work, and that we did show. The second was to improve the technology by about a factor of 10. Now, when you improve the technology by a factor of 10, you look 10 times deeper into the universe. That gives you, when you're far enough out, and we are already far enough out now, namely we are at a distance where we could see these things happening at a distance of about 30 to 40 million light years away. So we are already deep into the universe, where we're encompassing many, many galaxies. So if you improve the detector by a factor of 10, which is what we're in the middle of right now, when you come back on the air with that, we would expect to increase the rate by not 10, but 10 cubed, 10 times 10 times 10. That means a factor of 1,000. So instead of having one event in 10 years or one event in 30 years, it's somewhere in there, it would be 30 events per year. And that's what we're hoping for in the development of what we call advanced LIGO, which is a thing that has been funded and was part of the initial concept. So that's the best answer I can give you. I can't tell you how many of the other sources that, for example, that we may see black holes first, but I can't be as assured of the answer to you for those, because I don't know how many black holes of a certain mass there are in the universe. But I do know how many neutron star pairs there are in the universe, and well enough to make the statement I made to you.
And so with that, I'm going to close. Thank you so much, and thank you, panelists. And I hope you will all, over the next few years, hopefully sooner, be looking out for the radio report, and you will hear it for that distinctive sound, whoop. So please, like a Broadway show, Broadway musical, go out humming. Whoop. Thank you so much for coming.